Hi, my name is Daniel Chen. I'm a senior at the math department here at K. Today I'll be giving a talk on finite geometries and quantum systems. So today's talk will be broken into three sections. The first section will be on finite geometries. The second section will be on museum-biased bases. And the last section will discuss applications or comparisons in future directions. In section 1 and 2, we will aim to provide some preliminary definitions, interesting examples, and a cool theorem under some parallel structure. Then in section 3, we'll aim to tie everything together and discuss some neat real-world applications. So section 1, finite geometries. In the first section of our talk, we'll begin by introducing the incidence structures, which are critical to understanding geometries. After a quick introduction to incidence structures, we will move into projective planes and affine planes, identifying their incidence relation axioms, and providing some nice examples. We'll compare those guys and see if we can think about a existence theorem. So what is an incidence structure? Well, an incidence structure is a triple comprised of a set, a point set, a line set, and an instance set. The point set will be our umbrella set. The line set can be thought of as a collection of subsets of our point sets. And the set of incidences will be a subset of the Cartesian product between the point set and the line set, where each element of the instance set is a two-tuple, the first tuple being the point set element, the second tuple being the line set element. Most geometries we care about can be actually described as an instance structure. So here's an example of an instance structure. We'll throw down a set of points P, in this case P1 to P5. Then we'll throw down some line elements, L1 to L3, and we'll define them as subsets of the point set in a way that we've implicitly given our instance relations as so. So there's our first look at instance structure. But here's the thing. We explicitly decided to label these subsets as what they are. With another labeling, we can get the same structure. Here we've swapped L1 for L2, L2 for L3, and L3 for L1. Note that the geometric structure is preserved if we choose to relabel our points. In fact, it seems like we can arbitrarily label the lines here, and similarly the points, and we'll still have the same shape. So it seems as though the labeling of the points isn't at the core of our instance structures. And so what about the shape? Well, also in our example, we explicitly pick some positions for our points. So let's pick a different configuration. We'll scatter our points P1 to P5 as so. Then we'll define the lines with the same subsets, which then implicitly defines our incidence relations. Oh, so now our instance structure looks pretty different, but based off our definition, we still have the same lines and the same incidences. So those two structures must be equivalent. It seems like the position of points and lines is also not at the core of our instance structure. So we can also permute the labels and translate the points. We picked a new arrangement, here's a second arrangement, and then we can also rearrange our lines again. And we'll have, again, we'll have the same instance structure as our instance relations between points and lines are being preserved. So as long as our instance relations are being preserved, these structures are going to be equivalent. Well, what are some other actions that preserve instance relations? Well, here's our base case. And we've already discussed translating points and lines. And we've also discussed relabeling. So in this case, relabeling here is just picking some different color schemes for our points and our lines. We can also rotate and scale our structures, and this kind of comes for free from point translation. We can also have our lines be weird shapes and overlapping. What is important is that the incidences are still being preserved. So take the yellow line, for example, it's super jagged and overlapped itself at some points, but at the end of the day, it's still incident to those three same points. So as long as we have the same number of points, the same number of lines, and if our instance relations are preserved, then we're in business. In fact, we have a special name for these types of equivalences. We'll say that these instance structures are isomorphic. Also note that an instance structure can be thought of as a generalization of the simpler graphs we deal with in graph theory. In this case, an edge is contained or incident to more than 2 points. And we can add restrictions or conditions such that we are considering a more unique set of instance structures. So for example, a simple graph might require that an edge contains exactly 2 vertices. And so hence, by taking various axioms, we can form a partially ordered set of classes as instance structures. Let's look at an example of a non-isomorphic instance structure. Here we have S1 and S2 given as such, and note that they have the same point set, P1 to P5. They also have the same number of lines, L1, L2, and L3. However, we have an instance in S2 that isn't present in S1. Namely, that instance is P2 at L3. So P2 L3 is in the instance set for S2, but it's not in the instance set for S1. So what we want to point out here is that there can be 2 structures who have the same order of points and lines, but differ strictly by defined instance relations. Oh, also, we already said that S1 and S2 are not isomorphic. So say there were some parameters which could classify the size of an instance structure. It might be interesting to look at how many possible instance structures of a certain kind might exist given that size or order. Some other examples of instance structures include combinatorial designs, like the handshake problem. The points are the party attendees, and the lines are pairs of folks who have shaken hands, and the instance relations are handshaking. We can also talk about graphs, like the Peterson graph, or bipartite graphs. We can also talk about projective planes and affine planes. Our focus in this talk will be on the finite geometries, and in particular on projective planes and affine planes. So what is a projective plane? An instance structure is called a projective plane if it satisfies the following 3 axioms. The first axiom states that if a point P and Q are elements of the point set, then there exists some unique line L such that both P and Q are incident to L. In shorthand, we can remember this as any 2 points in the projective plane share a unique line. The second axiom states that if L and K are distinct elements of the line set L, then they share some unique point P in the point set such that both L and K are incident to P. In shorthand, we can remember this as any 2 lines in the projective plane share a unique intersection. The third states that there exists some 4-element subset Q of the point set P, such that no 3 elements in Q are incident to the same line. In shorthand, we can remember this as there exists 4 points in the plane, such that no 3 are collinear. I will also note that as opposed to axiom 1 and 2, axiom 3's relevance or niceness isn't so obvious. It'd be nice if we had some better understanding of this axiom, so keep this in mind as we proceed. So here's our formal definition of the projective plane laid out again as such, and we can very easily recall these axioms using our shorthand notation given here. Again, first, any 2 distinct points in the projective plane share a unique line. We can remember this as unique collinearity. Second, any 2 points, P1, P2, they must share a unique line. Second, any 2 lines in the projective plane share a unique intersection. We can remember this as unique intersection. And third, there exists 4 points in the projective plane such that no 3 are collinear. And we still need a better understanding of this, but at least we have a picture in our head now. We are also more interested in, these axioms both apply for the finite case and the infinite case of projective planes. Just keep in mind that we're more interested in the finite case. In the finite case, we can classify a projective plane by its order n, which we shall denote PG2n. You might observe that it's kind of weird that 2 is fixed. Well, with some generalization of our axioms, we can actually look at more general spaces called projective spaces, which depend on 2 parameters, namely the dimension d and the order n. In the case of the projective plane, we're in 2 dimensions, hence PG2n. Now we can use some nice combinatorial arguments to arrive at the following properties. Assuming that there exists some projective plane of order n, there will be n squared plus n plus 1 points in the plane, and n squared plus n plus 1 lines in the plane, where each point is contained in n plus 1 lines, and each line is contained in n plus 1 points. Note that there's some very, very nice symmetric action going on here. We have the same number of total points and total lines. Moreover, for each line and each point, there contains the same number of the opposing set elements. For those who have some experience in finite geometries, we might recognize the duality principle at work here. An interesting theorem that we won't go into too much depth in this discussion is that all projective planes are actually self-dual, which is pretty neat. So let's move on to some examples. We'll first look at the projective plane of order 2, denoted PG22, given here in the picture. In the upper left-hand corner, we've left the shorthand conditions for the projective plane, which one may check are satisfied here. The first 2 axioms are pretty reasonable, and we can check the box and crosshatch, which we saw with our third axiom, is present in any of those top 3 corners. We can look at them here, here, or here. It's also present in the set here, the triangle here, and we include this point here. It also forms a the set of 4 points also satisfies axiom 3. Okay, cool. Now we can proceed to check the properties. Here we have 2 squared plus 2 plus 1, which is 7 points of the plane. 1, 2, 3, 4, 5, 6, 7. And where each line is point, and where there's a total of also 2 squared plus 2 plus 1 lines, which is 7. 1, 2, 3, 4, 5, 6, 7 lines. Where each point is contained in 2 plus 1, which is 3 lines, and each line is contained in 2 plus 1, which is 3 points. And this is actually a very famous combinatorial structure known as the phonoplane. The second example we'll be looking at is the projective plane of order 3, PG23. Here again, we can check that our shorthand conditions hold. The first 2 are easy checks. For the third axiom, we'll also want to find that crosshatch and box geometry, which we see, with any of these 4 points here, like this, or maybe this points, or maybe these points, or these points, or these points here, or these points here. There's a lot of those guys here, which we can pick to find that box and crosshatch geometry. And so I guess how many examples of these are there? How many examples of this nice cross and box hatch geometry are there in this projective plane? The fun question you might ask later on for yourself is there a nice relationship between the order of the projective plane and the number of these third axiom subsets that exist? So moving on to addressing the properties of the projective plane. First, note that there are 3 squared plus 3 plus 1, which is 13 points in the plane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And there are also 3 squared plus 1 plus 3, just 13 lines in the plane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, each denoted with a different color, where we have that each point is contained in 3 plus 1 lines. This is a point, 1, 2, 3, 4 lines. And each line is contained in 4 points, 1, 2, 3, 4. No special name for this guy. So we've discussed a couple finite examples, but I thought it'd be worth touching on infinite examples. So Our projective planes can also be infinite, and actually we're pretty familiar with how the infinite projective spaces look and work. Anytime we really have a perspectival point or points that are not in our real space, we have that all these lines converge to this point. That's going to be a pretty good indicator for we're looking at some sort of projective space. And so for now, that's a pretty strong way for us to identify projective spaces. So let's move on to affine planes. Well, what is an affine plane? So an instance structure S with a point set P, line set L, and an instance set I is called an affine plane if it satisfies the following three axioms. The first axiom states that, it's the same axiom as our projective plane. If P and Q are distinct elements, then you have a unique element L in the line set such that P and Q are both incident to L. And so this is, again, unique incidence. For our second axiom, this one's slightly different. We're going to let a point P and a line L be given such that P and L are not incident. If this is the case, then there must exist a unique K, a line K, such that P is incident to K and L, the intersection of L and K, which are both subsets of the point sets, must be empty. In this case, we will call L and K parallel. And hopefully this is a pretty familiar definition for parallelness. If your two lines are not going to be parallel if they don't cross each other, so the intersection should be empty. Lastly, for our third axiom, there exists some three non-collinear points. Immediately, on immediate glance, it feels pretty cryptic, kind of like the axiom 3 of the projective planes. And again, we'll have some nice shorthand, which will make the conditions easier to recall. For our first axiom, we'll have that any two distinct points line a unique line. We can remember this as unique intersection, 2 points, unique line. For our second axiom, if a point does not line a line, then it must line a unique parallel line, shown there. And for our third axiom, there exists three non-collinear points. So let's drop 3 points, and none of them sit on not all three of them sit on the same line at once. Which, oh hey, that's just a triangle. So I guess that's not so cryptic after all. Well, I guess we can just remember axiom 3 as the existence of a triangle. Just like in projective planes, there are finite and infinite cases. These axioms hold for both, and we'll be focusing on the finite. In the finite case, we can also classify planes by its order n, which we shall denote AG2n. Again, with some generalizations for axioms, we can look at these general spaces called affine spaces, which also depend on 2 parameters, namely the dimension d and the order n. In the case of affine planes, we're in 2 dimensions, hence AG2n again. Now, we can also use some nice combinatorial arguments to arrive at following properties. Assuming that there exists some affine plane of order n, there will be n squared plus n, or n squared points in the plane, and the plane will have n squared plus n lines. It contains n points, and each point is contained in n plus 1 lines. Now, opposed to projective planes, we don't have that nice symmetric action going on here. We have differing lines, differing numbers of total lines and points, and also differing numbers of points in lines and lines in points. So again, we can use the duality principle here, but in this case, we'll say something slightly different. We'll say that our theorem is then that all affine planes are actually not self-dual, and they can never be self-dual. So now let's move on to some examples. We'll first look at the projective plane of order 2, denoted PG22. In the upper left, we've got the shorthand conditions for the affine plane, which one may check are satisfied here again. The first 2 axioms, reasonable check. The third axioms, we have 3 triangles to choose from, so axiom 3 is satisfied, or 4 triangles to choose from, sorry. Yes. Now we can also proceed to check the properties. Here we have 2 squared, which is 4 points in the plane, 1, 2, 3, 4. And we should have 2 squared plus 2, which is 6 lines, 1, 2, 3, 4, 5, 6. With each line containing 2 points, as shown there, and each point is contained in 3 lines, which is shown there. Cool. Recall that the instance structures are isomorphic, right? Earlier on, we discussed isomorphism under translation and permutation. So if we move D to the top right corner, it should still be isomorphic. And if we do some squeezing and moving around, we can notice that this is actually nice box and crosshatch geometry, which is the third axiom of our projective planes. So that means then our third axiom states exactly this, that there must be an affine plane of order 2 embedded into any projective plane of finite order. That's pretty neat. The second example we'll look at for the affine plane of order 3. Again, we will check that our shorthand conditions hold. The first two are easy checks. The third axiom, we have a ton of triangles to choose from. In fact, it's a fun game. Again, how many triangles, subsets of three non-collinear points, exist in AG23? So moving on into addressing the properties of the affine plane. First, note that there are 3 squared plus 3 squared line points in the plane. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there are 3 squared plus 3, which is 12 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And we have that each line contains 3 points, as shown there. And each point is contained in 4 lines. This combinatorial structure is also known and studied pretty well. It's got a special name. It's called the Hess configuration. And so we've discussed a couple of finite examples of affine planes. So it's also worth mentioning again that affine planes are also possible for them to be infinite. We're actually all pretty familiar with how infinite affine planes work as well, kind of like projective planes. Generally speaking, Rn is a n-dimensional affine space. Should we not give it a metric? That pretty much just means that we don't know where the origin is, or we've kind of forgotten where it is. This is a pretty familiar family of affine spaces, or we're pretty familiar with this family of affine spaces, as pretty much every math class before calculus 1 and 2, you're only operating in Rn for the most of it. So we've previously identified some interesting relations between projective and affine planes, namely that third axiom of the projective planes requires that an affine plane of order 2 must be embedded in its structure. But there's a lot more to talk about between the relationship between these two structures. So let's take a closer look here. So here's a nice table of all the examples we've looked at so far. We've already shown that AG22 must be embedded inside PG2N. And looking at this table, you might think to yourself, well, hey, wait a minute. The order 3 cases, it looks like, you can embed the affine plane of order 3 into the projective plane of order 3. And for the real cases, I mean, you might have this sense of embeddedness also, right? You kind of walk through this 3 space, but you kind of see this other 3 space too, right? So it feels a bit intuitive for them to be embedded as well. And, if this is your intuition about these things, then, you'd be correct. Every time there exists a projective plane of order n, there actually exists an affine plane of order n. In fact, there's an even more powerful theorem about this, and that's this. Our theorem states that if there exists a unique affine plane of order n, then there must also exist a unique projective plane of order n. So not only do we have a statement about constructibility, but we also know that a unique affine plane corresponds to a unique projective plane. Unfortunately, the converse doesn't hold. So you might ask, well, Daniel, how the heck do we do this construction? Here's the algorithm. First, we'll take some projective plane of order n. Then in the plane, we'll pick an arbitrary line. Recall that the projective plane is extremely symmetric, so it really doesn't matter which line we pick. We'll delete its incident points, and then for aesthetic purposes, we can push the tails of the lines into the nearest point. And that should make us an affine plane. So let's try it out. We'll begin with the final plane. So we'll take some projective plane of order n. This time we'll take order 2, right, the final plane. We'll pick an arbitrary line. So let's pick the inscribed circle, and we'll delete the line and its incidence points. So bam, bam. Oh, sorry, bam, bam, bam. We'll then push those tails of those lines into the center points, just like so. And doing this, we've just constructed the affine plane of order 2. Again, we'll take some projective plane of order n. In this case, we've taken it to be 3. So we'll pick a line, say the gray line here, delete the line and its incident points, bam, 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 bam. And then we'll push those tails into the central points. So just like so, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we'll be left with this structure. Turns out that this guy is actually isomorphic to the Hess configuration. So the orange line goes there, the red, the yellow line goes there, and the blue line goes there. You feel free to double check this and trace the lines yourself. Cool. So that's pretty much about it on the constructability of these ordered planes, planes of order n. Note that all this time, right, we did assume something that, for all these properties and theorems and constructions, we've assumed that there has existed a projective plane or affine plane, but we can't take this for free in every case or for every n. For example, in 1959, it was actually shown that there can't exist a projective plane of order 6, and hence there can't exist a affine plane of order 6 as well. So when do these planes exist? Well, besides the case for n equals 6 or 14, we actually don't know when they do or don't. Well, we don't know if they don't exist for particular cases. But at least for some cases, we know that they do exist for some n's. And we have a nice theorem for which specific n's too. And here it is. There exists some finite projective planes of order n for all prime powers n. So the proof about this theorem actually comes from, there's two directions of this proof. There's mutually orthogonal Latin squares, which we won't touch upon so much, but you can look up on your own. And we also have this nice vector space construction using finite fields, which we'll talk about a bit more later on. By our construction algorithm, immediate corollary is that there exists a finite affine plane of order n also for prime powers. The existence of finite projective planes and finite affine planes of non-prime power order is still an open question, although it's conjectured for the most part to not exist. So here's a summary and touching upon some meta mathematics. Throughout this section, we started out by identifying some elements of sets and talked about a pairwise relation which belonged to a mathematical object, or which gave us a mathematical object, right? We looked at a point set and line set and the incidence relations, which gave us the incidence structure. We looked at a point set and line set and projective incidence relations, which gave us projective planes. We looked at a point set and line set of affine incidence structures, affine relations, incidence relations, which gave us affine planes. With each object, we unpacked some definitions and examples, and we connected all of these topics to each other. We answered the following two questions also. First, when do finite projective planes and affine planes exist? And second, how can we classify and construct these guys? And so that kind of wraps up our first section on finite geometries. So moving into section 2, we'll be talking about mutually unbiased bases. So here's a breakdown of section 2. We'll define inner product, orthogonality, and orthonormal basis, mutually unbiased bases, and we'll probably provide some examples connecting topic to topic like we did in section 1. We'll then finish up by providing an existence theorem, which is eerily familiar to what we've seen in section 1. So what is inner product? Given some vector space V, an inner product satisfies our following four properties. For our vectors u, v, and w, and a scalar c, first we have that the inner product of u plus v equals to the sum of the inner products of u and v and w. The second property states that the inner product of a scaled c, a vector cv, and a vector w is equal to the inner product of v and w scaled by c. Together, the first two properties make up what we call bilinearity in the first term. The third property we have is that the inner product of V and W is equal to the conjugate of the inner product of W and V, where typically when we say conjugate, we mean complex conjugate. Note that for real vectors, the complex conjugate of a vector, or for real elements, the complex conjugate is going to be itself. We call this property the symmetric property of inner products. Lastly, the inner product of a vector and itself is always greater than or equal to 0. And equal to 0 if and only if V itself is a 0 vector. This is the positive definite property of inner products. So those are seemingly a lot of new properties, but rest assured, I promise to you this is a familiar concept. The inner product is essentially a generalized dot product. So let's consider some vectors u, v, and w in R2, which we are familiar with, and let's let C be 2. So here's u, v, and w. Recall that our standard dot product is defined as the sum of the component-wise products, or the product of magnitudes and the cosine between the angle of vectors. Our first property states that u plus v dotted with w should equal to u dot w plus v dot w, which we can see here, right, visually. So let's add u and v together to get this blue vector and project that onto w, like so, which we get this red bar. The projection will be proportional to the dot product. That's just part of the definition of projections. So we'll project u onto w and get this little orange bar, which will stick right there for the time being. And then we'll project v onto w, which will get another orange bar. And when we add the two together, we know that they're actually the same length. So those guys are equal. Cool. For our second property, the scaled dotted v, the scaled v dotted with w should equal to the v dot w scaled by c. So we'll first double our vector v, then we'll project it onto w, get this red bar here. Then we'll project v onto w and then double its length. And would you look at that, we get the same thing. Cool. So that property holds as well. And that's bilinearity. Note that by the commutativity of real numbers, we actually get the symmetric property for free. And 4 just kind of makes sense. If our vector is non-zero, I'm definitely sure we'll have a length. I'm positive of that. Ha ha ha. So the key idea here is that the inner product informs us of the angular distance between vectors, or how much one vector kind of projects onto another. But we can think about this as how similar are vectors. We're mostly concerned actually with the complex inner product, as quantum mechanics happens for the most part in complex spaces. In our one-dimensional case, for two vectors v and w in the complex plane, the inner product is defined as the standard dot product between the complex conjugate of v and w, where we're looking at just the real and imaginary parts. So it's just the real part of v times the real part of w plus the imaginary part of v conjugate plus the imaginary part of w. In our d-dimensional case, we'll do this the same for each dimension and sum them up like so. Now we have some foundation for understanding the inner product and how to compute it and what it looks like in terms of projections. So we kind of have the tools to discuss orthogonality now. So what is orthogonality? Well, two vectors z and w of some finite dimensional vector space is called orthogonal if the inner product is equal to 0, denoted as here. Note that our inner product is predefined over a vector space, so actually we're dealing with an inner product space. This is just a careful, small notion to mention. Let's look at some examples. Looking at our standard dot product in R2, we know that if the dot product is 0, right, then the angle theta between the two vectors must be 90. Or negative 90, It's pretty much just 90. In fact, this holds true for all Rn where n is finite. Geometrically here we have that V and W, right? We'll have some V and W just like so, and we'll have some nice perpendicularity. Here's a computational example in C2. So taking the complex inner product of these two vectors, one I and one negative I in C2, we have that their sum is actually just 1 and negative 1, which is 0. Cool. So these vectors are actually orthogonal to each other as well. So orthogonality can really be thought of as a generalized perpendicularity where vectors are as independent as possible from each other. So what if I fixed a vector? If I knew the dimension of the inner product space, could I know how many pairwise orthogonal vectors existed in said inner product space? So this leads us directly into our next concept of orthonormal bases. Let some set of pairwise orthogonal unit vectors E1 to ED of some finite d-dimensional vector space be given. We'll call this set of D vectors an orthonormal basis if for all I not equal to J, so distinct I and J's, we have that EI and EI, the inner product between EI and EJ is 0, and the inner product between EI and itself is 1. Note that we have a set of elements, right, we have a pairwise relation, namely orthogonality, where each vector is a unit. It's normalized, and we capture, right, the orthogonality by saying that inner product between distinct vectors is 0, and we could capture normality by saying that the inner product between a vector and itself is 1. So more compactly, actually, we can just say that the inner product between any two vectors is actually just the Kronecker delta. Hello, my physicist friends. Cool. So let's look at an example. So we're back in the real 3 space. We'll pick some unit vectors on distinct axes, x, y, and z. And based off this, we'll have an orthonormal basis because they're all 90 degrees apart from each other, which we kind of learned all throughout calculus and wherever else. This basis will be called our standard basis or computational basis. Okay, so then let's pick a different color and rotate the basis such that the angles are preserved. Note that this is still an orthonormal basis because the inner product relation still holds. The angular distance is still preserved. In fact, we can actually rotate. We could have rotated our standard basis at a whole host of angles, right? We could have rotated by infinite number of angles. And so there must be infinite distinct orthonormal bases given a vector space, which is pretty neat. But which ones are kind of nice to each other? So let's take a look back at the relationship between our standard basis and our new basis. They're spaced pretty nicely apart from each other, so we can tell the difference between them pretty well. A question you might ask then is that, is there a nice pairwise relation for orthogonality that can help us distinguish between orthonormal bases? Surprise, surprise, there is a nice pairwise relation, and that's called mutually unbiasedness. Finally, we have all the tools we need to talk about mutually unbiased bases, so let's get cracking. Let two orthonormal bases E and F be given in some finite d-dimensional vector space V. If E and F are called mutually unbiased, if the magnitude between if the magnitude of the inner product between any two vectors from different orthonormal bases is actually just 1 over the dimension D. So fun note, we'll actually be wanting to talk about a Hilbert space here, which is just an inner product space that's complete, and that just pretty much means that you can do all the nice computations that we want to. For our quantum theorists out there, we might recognize that the inner product squared as the probability of measuring a state vector EI from a state vector FJ. So this notion of a fixed outcome with the same probability regardless of which eigenstate or nice vector you pick, right, or you end up measuring, right? Vectors. This notion of a equally probable measurement of any of these eigenstates given a fixed input is where the unbiasedness comes into play. But what do these orthonormal bases look like with respect to one another? Is there a nice way of visualizing them in space or geometrically? So here's an example. Let's be in R2, okay, which is isomorphic to C, and consider the following orthonormal bases. We'll look at the standard basis here, and we'll look at the orthonormal basis rotated at 45 degrees, given here in yellow. Next, we can take the inner product of each of these pairs of vectors, right, from opposing bases, and they all end up being 1 over the square root of 2 or negative 1 over the square root of 2. So we can just kind of verify that their magnitude squared is really just 1/2. In fact, given a standard basis in R2, we can only squeeze one more distinct orthonormal basis such that it will still be pairwise mutually unbiased. So this is a maximal set in a sense, because I can't put any more mutually unbiased bases in here. So geometrically, bases are mutually unbiased if they're pairwise nicely spaced out over some angular distance. In some sense, we could say that the yellow vector is equally close to x and y, the x-axis and the y-axis. And it also turns out there's a nice way to encode our mutually unbiased bases using matrices, which I'll show you here. So here's how we do it using matrices. First, we recall that given a set of eigenvectors and eigenvalues, we can construct a matrix by taking the matrix product P lambda, P inverse, where the columns of P are eigenvectors and lambda is the diagonalized eigenvalue matrix. So we'll just pick some nice eigenvalues and the matrix. Just pick 1 and -1 for our eigenvalues. Then since P is the identity, our matrix is really just the diagonalized eigenvalue matrix given here. And it makes sense that our corresponding matrix from the blue basis is diagonal because our blue basis is the standard basis, right? For our yellow basis, again, take 1 and -1 to be the eigenvalues. Then set up the following equation, like so, throw it into a matrix calculator, and you'll get 1/2 of this matrix here, which is just proportional to this matrix here. Just keep these matrices in mind. Cool, so we've encoded each orthonormal basis into a matrix given here and here. And then by taking this set of matrices, we have found a set of mutually unbiased bases, right? Because the corresponding eigenvectors form a orthonormal basis, and now we got a set of those guys too. So there's also a nice generalization of matrices which we can use to further encode our orthonormal bases, which are called operators. But that's kind of a bit beyond the scope of this talk. Now, while this example is nice and simple, it doesn't exactly pan out in any obvious manner to any useful applications, like immediately speaking, right? The physical space in which we operate is in 3 real dimensions at least, right? So what about higher dimensions? And what about complex spaces? Because we really care about complex spaces, because complex spaces is where all the quantum stuff happens, right? Like how many MUBs can you squeeze into a d-dimensional Hilbert space? Well, for any d, that's the exact number of MUBs that can fit into a d-dimensional complex Hilbert space is still an open question, but we do have nice bounds for all d, which I will share here. So here's the theorem. Let MD, M of D denote the net maximum number of mutually unbiased bases over a finite d-dimensional complex Hilbert space with the prime decomposition of D given as such, where D equals to P1 to the N1, P2 to the N2, Pk to the Nk, where they're all kind of ordered such that it's littlest to biggest, right? Smallest to greatest. And then for a maximal set of mutually unbiased bases over CD, we know that it's bounded below the number of mutually unbiased the number of mutually unbiased bases in a maximal set is bounded below by P1, N1 plus 1, and bounded above by the dimension plus 1. Hey, we've seen that somewhere before, this D plus 1. This has been proven using 3 different methods: while operators, Hadamard matrices, and unitary operators with finite fields, which Swedish mathematician and physicist Ingmar Bengtsson of Stockholm University provides in a paper circa 2004. For the most part, they rely on operator algebras, while operators, Hadamard matrices, unitary operators under the Galois transform. There exists also construction algorithms, which Bengtsson mentions, the easiest to understand from an undergraduate level being unitary operators in the Galois transform. But this is kind of outside the scope of our talk as well. But you can feel free, I'll leave some sources at the end of the talk, which you can also reference to look into these more on your own. Okay, so now we have, we know what these bounds are. We have a lower bound and upper bound. So maybe your next question is, when is that bound saturated? Well, for our keen-eyed viewers, right, that bound will be saturated when there is only one prime power, right? So that means that when D is a prime power, there exists a maximal set of D plus mutually unbiased bases in a D-dimensional Hilbert space. And this is a pretty natural conclusion, but pretty interesting too, because we've seen that prime power come up somewhere else before, right? Okay, before we move on, let's look at another example, right? We know 2 is a prime power 2 to the 1. So let's look at C squared. For our quantum theorists, I bring your attention to the qubit or the spin half system. In C2, it turns out the Pauli matrices actually form a maximal set of mutually unbiased bases. So as a reminder, the Pauli matrices are sigma x, sigma x, and sigma y. The eigenvalues or eigenvectors are given as here. So here are the eigenvectors for sigma z, here are the eigenvectors for sigma y, and here are the eigenvectors for sigma x. In each case, we're in C2, or in this case, we're in C2. So we expect the inner product for any 2 vectors from distinct bases to be 1 over 2. Feel free to double check these computations and convince yourself that these form a maximal set of mutually unbiased bases. Cool, so that pretty much wraps up your section, but let's talk about a summary, and let's go through a real quick summary and some metamathematics. Throughout this section, we started by identifying some elements of a set and a pairwise relation which belong to a mathematical object. We looked at vectors and orthogonality, which gave us an orthonormal basis. Right? We then looked at orthonormal bases and mutually unbiasedness, which gave us a maximal set of mutually unbiased bases. And with each object, we unpacked a definition, provided some examples, and connected them to each other. We also answered the following questions. First, when do maximal sets of mutually unbiased bases exist? And second, how do we classify them? And so that finally wraps up our section on mutually unbiased bases. So now we're in the final section, comparisons and future directions. So we'll just talk about the existence theorem, compare it really quickly, talk about some finite field and vector space, and talk about this MUB polytope, and talk about some applications. So from finite geometries, we have that our theorem 1.7 states that you got finite projective planes, order n, if n is a prime power, and our corollary states that you got affine planes of prime power as well, for if n is a prime power, right? From mutually unbiased bases, we have that the upper bound is saturated if D is a prime power too. So what is up with these prime powers? Well, there's a classic theorem from field theory that tells us that all finite fields are of prime power order. And this is relevant to us because with some field theory, we can have that vector spaces are field extensions, okay? And we can also describe finite projective planes and affine planes using vector spaces and finite fields. In the case of vector spaces being field extensions, the vector elements are actually just the elements of the field extension, and the scalar elements belong to that fixed subfield. And with these tools, we can actually embed a projective plane into or an affine plane into a vector space, which is kind of neat because we've just placed a geometrical object in an algebraic representation. Conversely, in spite of being an algebraic object, MUBs are really all about the geometry of nice vector spaces. So here's an excerpt from a paper on MUBs. I think this is Bankson, and it brings up this nice operator, which is constructed using MUBs. And there are those familiar numbers that we see again from affine planes, right? It turns out that there are a total of d squared plus d vectors, right? And in this case of this algebraic object, which is brought up in the paper, there are d squared subspaces of dimension d, where each subspace contains d plus 1 vectors, and each vector sits in exactly d subspaces. These numbers are really, really familiar, and they're familiar for one reason, because they're the exact same numbers for the properties of the affine plane. So this construction of the object, this object is like really, which is related to the maximal set of MUBs, right? Is basically an affine plane. So now we have this pure geometrical notion of this pure algebraic structure. What are some applications of these guys? This is actually a very young idea. It was introduced by this guy named Schwinger in 1960, and its first applications were only first considered in the early 1980s by this guy named Ivankovich. Since then, there have been a lot of applications of MUBs, predominantly in quantum system-related fields. For example, in quantum information theory, quantum computation, quantum mechanics, quantum field theory. In particular, there are uses for MUBs in quantum state determination and quantum state reconstruction. Remember that from quantum theory, all states of a system are a nice linear combination of eigenstates of the system, and each eigenstate corresponds to a vector. With this in mind, it's useful to have a nice set of vectors, maybe an orthogonal basis, to use as your basis of measurements. Recall that also incompatible observables on a system that you'd like to measure, which will have non-commuting matrices, which will give us the eigenstates, right? So take for the classic examples, right? The position, momentum operators, or the spin operators in x, y, and z directions. So for that reason, right, because you want to do these multiple measurements over different these different operators, right? You want to, over these different observables, non-commuting observables, you want to have these multiple orthogonal bases that play nice with one another. When we also want to make randomized or unbiased measurements, we can take an arbitrary vector v from an orthogonal basis, right, and find a orthogonal basis that's mutually unbiased to it, such that by the definition of our mutually unbiased bases, that arbitrary vector v will be equally probable in any of the states. It'll be equally probable when we measure it to be in any of the states of the mutually unbiased bases. The other operator that's mutually unbiased to it, right? And the last use I'll mention is for detecting entanglement in systems. So what's next for me? Well, what I'll be doing moving forward is trying to learn more about operator algebras, and each proof of the mutually unbiased basis existence depends on these guys, and it's really a dense field. Hopefully by doing some work and getting some insight, our reaching goal would be to prove that the upper bound is unsaturated for composite dimensions. I'd also like to examine some more applications of mutually unbiased bases for dense coding. And then lastly, I'd like to work on this kind of stuff in grad school. So here are the resources that I referenced during the presentation. And that's pretty much all for my talk. So thanks for stopping by and listening.